Hello and welcome to the Rankine Cycle, which drives global electricity generation. A brief history. Newcomen's atmospheric engine of 1712 brought together a number of previous inventions dating back to Rome and Egypt. Watt, building on this, developed the Watt engine in 1774. The first high-pressure steam engine was invented by Richard Trevithick in 1800. William Rankine is responsible for developing a complete theory on the steam engine, known as the Rankine Cycle, in 1859. Key definitions to understand throughout this video are entropy, the degree of disorder within a system; isentropic, to have equal entropy; isobaric, to have constant pressure; and finally adiabatic, a process occurring without transfer of heat or matter. Key facts. 80% of electricity generation is the result of the Rankine cycle and steam turbine generation. This is predominantly used in coal and nuclear power stations, however there are many renewable applications. The organic Rankine cycle optimizes renewables and could play a large role in the future energy mix. What is the Rankine cycle? It is an idealized thermodynamic cycle of a steam heat engine, converting heat into mechanical work while undergoing phase change. Power performance is dependent on the temperature difference between the hot source and the cold source. Why is the Rankine cycle used? The Rankine cycle is an adaptation of the Carnot cycle. The Carnot cycle is more efficient, however only theoretical, and it is not possible to achieve the ideal conditions in power stations. As a result, the Rankine cycle is used. The following animation shows the ideal Rankine cycle. We can see from steps 1 to 2 there is isentropic expansion of the working fluid, which allows steam to turn the turbine. From 2 to 3 there is isobaric heat rejection in the condenser. From 3 to 4 there is isentropic compression by the pump requiring external force raising the pressure, and 4 to 1 there is isobaric pressure heat addition. However, this is not possible as there are losses throughout the system, which we will discuss later. Superheating. The Rankine cycle can be enhanced with the use of superheating. This involves heating the fluid past the point of vapor saturation. Increasing mean temperature of the heat addition improves efficiency and power performance. Less moisture content in the mixture reduces the rate at which the turbine blades deteriorate. The following animation compares both the ideal and actual Rankine cycle. We can see that the main differences occur between phases 1 and 2, where there is a pressure and heat loss. Expansion is non-isentropic with entropy generation and heat losses. From 2 to 3 there is heat loss with a frictional pressure drop. From 3 to 4, pressure increases by non-isentropic pumping and inefficiencies as a result of heat transfer. And finally, from 4 to 1, there is further heat addition with a frictional pressure drop. The condenser in both this animation and the previous are the large cooling towers you can see in power stations. The first experiment involved a simple drinks can. 2 holes were pierced either side with the addition of water. As heat is applied, we can see that steam is generated as a result of the phase change from liquid to gas. I think this highlights how simple steam turbine generation can be. In the second experiment, using the same drinks can, an organic solvent was used. We can see that the same force is generated, however at much lower temperatures, as the heat source is placed further away, and this is how the organic Rankine cycle can be harnessed. The organic Rankine cycle uses an organic high molecular mass fluid with a boiling point occurring at a lower temperature than the water and steam phase change. It allows Rankine cycle heat recovery from lower temperature sources. The low temperature heat is converted into useful work, which in itself can be converted into electricity. As this happens at lower temperatures, there is no need for superheating. Renewable applications. This includes biomass combined heat and power, geothermal, concentrated solar plants, waste heat recovery, and heat recovery on internal combustion engines. The dipping bird experiment with the use of organic solvents helps to highlight the ability of a heat engine to be able to extract motion from low temperatures. This is how the dipping bird experiment works at room temperature. The following hand boiler experiment helps us to further understand the importance of organic solvents and how a phase change can occur at much lower temperatures. As we can see, as body heat is applied to the bottom of the hand boiler, a phase change begins, and we can see that the organic solvent actually begins to boil. Summary. Steam turbines have played an important role throughout history and modern-day electricity generation, being partially responsible for the Industrial Revolution. Understanding the Rankine cycle allows for optimization of the system. The organic Rankine cycle has many renewable applications. The organic solvents used allows for the process to occur at much lower temperatures. These renewable alternatives may offer a solution to reducing carbon emissions and reducing the use of fossil fuels. Thank you for listening to my brief introduction to the Rankine cycle. I hope this has helped illustrate the importance of modern-day steam technology.